Okay, everybody ready? That's 3 seconds before it starts. It's like you can take a deep breath. How's everyone?
Good.
Good. Thank you again. I have to do it on. If it doesn't happen on the recording, it doesn't happen. Right? So this goes online, and we can double confirm that it's now in the record that we are all good. Even if you're not good, that's the way. That's customary here in America. We ask how you doing, and everybody says good. All right. Unless you're in the South. Anyone from the South?
What are they saying?
South, deep South. I used to live in Georgia, and then people would say, if you ask how someone's doing, you better have 20 minutes. Right? Like it literally is. Oh well, I was doing pretty well, but my cousin called, and anyway, not to pick on that. Yeah, it is kind of more of a matter of speaking for me than it is anything else. But I do want to know how you're doing. I want to thank you all for the hard work you're putting into the class. I can tell you're all working. And one of the reasons for the quiz today was, first of all, that chapter had a lot of terminology into it. It's a mess. And second, we're talking about matrices and math statistics and things that seem like not SEM, even though it is, believe it or not. We've actually done a structural equation model already, and you don't even know it yet. Maybe you do. But so we're kind of building up toward where we need to be. So I don't want you to lose focus or interest in the class. It's not going to. I don't want to leave you behind. If it's none of this is stuff that you probably came to take the class on. If you're struggling, if you've got it all, even better. Awesome. You can teach me then. But I don't know that. I don't know that the way that is. What I'm trying to come up with is the homework that we're working on. Have you looked at homework 2 a little bit? That thing's a monster. I put it together, and let me give you the backstory for it, right? So my thought is with the homework, I want you to have a conceptualization of these likelihoods and these matrices and how they all go into it. That's where the homework is coming from, right? So the first part of it is like distributions. Plug in a number, get a height. Plug in a number, get a height. And the second part of it is a sort of model comparison. And both of those are going to be what we're doing as we go forward. Although the distributions, we're not going to plug in heights. I just want to show you where they're at. I want to have a mental representation of it. And I normally do this. I've done this in different classes. This is really how I start multivariate classes too. And because SEM is essentially a multivariate method, multiple variables in an analysis, this is kind of has a common part to place to start. This shows up now in front of SEM. I had it so that I used to give out a homework a week rather than every other week. And this homework 2 was actually 2 separate homeworks. It was like, oh, the first week do this and the second week do that. And so when we put them together, it may seem like there's an interaction between the two and becomes even more insurmountable. It may take a while. But let me back up and just take a look at homework 2, walk you through what I'm thinking with it, walk you through maybe a better example than what's online, and then answer any questions you may have about your own syntax or things that I can help you with. Okay? Cool. So homework 2's document. Here we have 150 flowers. So our sample size is 150, but each flower gives us 4 measurements. Actually, the species of the flower is like a 5th measurement if you want to think about it, but we're only going to be concerned with 4. The 4 quantitative measurements: petal, something about petal measurements, width and length. Does anyone know flowers? Do you know what a sepal is on a flower? Anybody? I actually had somebody in like biology take my class once, and she's like, "Oh, that's it." So I'm going to go and we're going to ask my friend Google. Okay, Google. Oh no, do I not have the audio? Darn it! Oh, there it is. Okay, Google. Maybe allow. Okay, he's coming. Stop. Coming. Oh gosh. Oh, no. Okay, Google. Define sepal. It's not telling it me. But
Sepal.
Sepal. Each of the parts of the calyx of a flower, enclosing the petals, typically green and leaf-like. Oh, we've got all these nice. Look at that. I love the data on it. I just want, why didn't it tell me that, you know? Okay, Google, why don't you talk? Question? Okay, never mind. Google errors. Pardon the technical glitches. So the point is, in multivariate data, it's exactly what we have. We have multiple observations from multiple measurements from a single observation. So the flower, each flower that we have is the observation, and the 4 lengths and widths are the measurements from it. Cool? All right, good. So the first step is to go and get an estimate of the saturated mean vector and the saturated covariance matrix for 5 of these flowers. All right? That is the code that we sort of have been building toward in our analysis, in our work with Livan. But the way that you can get a hold of it, you can essentially use this syntax I give you below here without the cov star in front of it. I don't know if you see that. I have every variable listed there. I have sepal length double tilde. What this does is it says to Livan, I want to estimate the covariance of sepal length and everything that shows up to the right-hand side of that double tilde. Right? So for now, just look at, don't ignore the thing in parentheses times, the cov times. That means sepal length. I want the covariance of it with sepal width. This plus symbol there is a little bit of a misnomer. You're not adding anything. It's not like a prediction model. It's the only way that Livan will recognize multiple observations on the other side of the double tilde. At least I found it to do. I've done this and it's broken, and so I take out the. I've done it without the addition symbol, the plus sign, and it worked. So, I mean, it didn't work. Pardon me. So I've used the plus sign. So I want the covariance of sepal length with sepal width, petal length, and petal width. Right? There's 3 of them. Now the next line down, you've got sepal width. Well, we already have the covariance between width and length. I just need the other 2. Sepal width with petal length and petal width. And then finally petal length with petal width. All right, so if you take this syntax verbatim with the exception of the cov times, that will answer question number 1 for you. Now, I want to note one thing about that in question number 1. I had before the likelihood, the log likelihood that spits out of Livan. There's actually 2 of them. There's the H0 user model, and there's the H1 model. If you put all 4 of the variables into the analysis but don't quite get the covariance matrix right, the H1 model will equal 26.805. In fact, that's what we're talking about today. H1 is always the saturated model log likelihood. And why that is, we're going to kind of get to today. But that shows up. What you want it to be the case is that your model, the H0 user model, is 26, the log likelihood is 26.805. Should be negative 26.805. Oh no, it's 26.805. It's actually positive in this one. Yeah. How are we doing? So far, so good. Did you have questions on that one? Question 1. Okay. So next, the hard part is I want you to, my thought in question 2 was I want you to visualize as much of this as you can. I'm a very visual learner, and when it comes to these math terms, I feel like it helps provide a mental representation of something that is absolutely far away from anything that we see in real life, right? And so plotting the PDF of the normal distribution is the idea of visualization. I thought, okay, for each one of these 4 flower measurements, we could take the mean and the variance of each that came from Livan and draw in R a PDF of it so you can see the distribution, and if you were to conceptualize each value that would go into it, each actual measurement of that variable, you can kind of see where their heights would be relative to each other on it. That's what I was thinking in building that question, just to try to provide that mental representation. Now, the actual practice of it may be a little bit more difficult. Let me give you a couple steps on how to plot here. I've got R up Can you? Hopefully you can see the syntax, and hopefully you can come back to this part of the lecture if you are looking to do this. The first thing that we need to do is get the mean value and the variance of a flower. So let's imagine you look at your Livan syntax or your Livan output. You've got it to run. You check the H0 model. It's equal to the right log likelihood. It checks out. Let's say we're starting with sepal length. All right. You go to the mean for sepal length and you grab its value. All right. So you just literally take it, look at it, take the 3 digits, and I'm just going to type it here. Mean equals. Does anyone know the mean of sepal length for those 5 flowers? Anyone have it? You can help each other. 4.86. Thank you. So there's the mean for sepal length. Is this sepal length or sepal width? Sorry. Sepal length. So I'm going to call this mean of sepal length. And then what is the variance of sepal length? 0.118. Okay. So you get those two numbers and you're in business. The next question is you've got to draw this plot across the x-axis, right? So here's the part in R that becomes a little bit more complicated. And the code that I put up online was probably too nuanced to really disentangle each part of it. So let me try to step through it. To draw this graph, you have to give it a range. You're trying to plot something on like the y-axis. So you have to go through a range of values on the x-axis. So I'm going to create a variable called x here. And I'm going to give it that range. R has a built-in function to give you a range. It's called SEQ for sequence. There's actually other ways of doing this in R, so if you found a different way to do this, awesome. You probably can teach me, but here's a good way of doing it. Sequence. Now the question is, where do we draw that range? Right? We could probably draw, oh my gosh, we want to draw something that's, between negative and positive some value. And the reality of it is, if you remember the normal distribution a little bit, do you remember where most of the values fall in the normal distribution? Standard deviations, yeah. So between plus and minus 3 standard deviations from the mean, you get some 99% of the values of the distribution. So that's sort of the range that we're starting to think about. We may go a little bit further on one way or the other. I'm not looking for precise. It doesn't have to be. I just want you to have a picture to represent it. So what is the standard deviation here? Let me do some values. I'm very bad. The standard deviation of sepal length is the square root of the variance. And that happens to be 0.3435, right? So let's just say we want to do plus or minus, let's say 4 standard deviations, right? The sequence function will give you that. It'll start x. It'll say I'm going to give a value for x, and I'm going to start it at the very lowest. And then I'm going to go up in increments to the very highest value. So the arguments or the numbers that you put after SEQ, open parenthesis, you put the lowest value. The lowest value we want is the mean sepal length minus 4 times the standard deviation of sepal length, right? We want 4 standard deviations below the mean, which really is a value of 3.845955, right, on the bottom there. That's the lowest value. So the highest value essentially looks the same. It's not negative or minus 4, it'll be plus 4. Oh. So quick note about going fast. I don't like to use the mouse as much as possible, so there's a lot of hotkey shortcuts in RStudio, and one of those that's very handy to know is the control enter function submits a line of syntax to R. So a line being where by default where the cursor is. I can highlight a line and it will just, if I hit control enter, it'll just run that segment itself. So if I hit control enter, you see at the bottom it submitted the highlighted portion and it gives me the result. So I'm going to get a sequence of values between 3.48 and 6.23. The next question is, there's one last little part to the sequence function to put in, and that is what step? What's the increment? And here it gets a little, you can pretty much pick anything that's a decimal. I would probably put 0.1 every tenth of every 0.1 segment more. What that represents a tenth of an inch. And what that really does is it talks about the resolution of the plot in the y-axis. If you pick too big of a step size, you'll have a very jagged plot. It won't look like a normal distribution. It won't be smooth. If you pick too many, it just may take a while to draw, but it'll look very nice and precise. So if I run this entire command here, which I can do by hitting Control-Enter on it, it runs that whole thing. It doesn't look like it gave me anything, but let me just show you. X goes from 3.48 all the way to 6.18 in 0.1 increments. All right? So for every one of those x's, I would like to draw the height on the normal distribution with the mean and variance of that flower. And that's where the Dnorm function comes in. Right? The height function what happens with Dnorm, if you remember the Dnorm function, I'm just going to type it here. Dnorm gives you give it x, you give it, what you're plugging in, the value of the data, the mean and the standard deviation, and it gives you the height of the normal curve. So here, the data are the hypothetical values on the x-axis. Right? So each one of those numbers that you see on the screen down there is a hypothetical measurement of sepal length for a flower. Right? So we have to go and plug all of those into the function. Luckily, R will do that automatically if we just give it the whole thing, the whole set, X. It'll do that for every single one of them. So we don't have to do multiple lines of code for this. The next part of this is you tell it the mean. I sometimes like to type the word mean afterwards. It's the name of the argument, but it's equal to mean SL. That was 4.86. And then the standard deviation comes next, and that was equal to SDSL itself. So if I run all this syntax, because I did not set it equal, I didn't set y equal to this right now, but if I just run this, what you'll see is all of these numbers, these little tiny numbers here. This corresponds with the height on the y-axis of the normal curve for every one of those hypothetical measurements of the flower. Is this helping at all? Awesome. Okay. Questions? Please stop me. I'm on a roll. You know how I get. All right. So what I'm going to do is backtrack just a bit and save all of those as y. Right? So if I save all of those as y, it's now in R's memory, which you can actually see over here. In our values section, you see x and you see y. Now I'm going to use the plot command in R. The plot command, you may have seen it in my syntax. Also, if you go on the right-hand side, the bottom right of RStudio by default, you can find a little help box. I actually think help should be in quotes. It's not really help, it's more just like extra confusion, but it does tell you what each of the things that happen in the parentheses should be, more or less. So you can put plot in here, and it will tell you generic X and Y plotting. That's really what we want. X, Y, oh yeah, and other things. That's why it's help in quotes. There's a lot of other things there, but in my syntax, you probably would have seen the plot function. So I can type plot. I need to give it X, the values on the X-axis. Well, that's just what I've saved as X. I need to give it the values on the Y-axis. And if I did that plot, what you'll see is I will get a graph that looks like a normal curve, or should. Come on, you can do it. There it is, but it's with circles. And there we go. That almost looks like what I want. The next thing, there's one little catch. That would be fine. I'm not looking for perfection on your graph. I just want you to see it. But one thing that you can do to make it a straight line is after the Y part on the plot command, you can say type equals, and in quotes, put a lowercase l for line, and that will give you the plot itself. Now you'll note there's a little jaggedness up to the top of it. Right? That's only because my step size in the increments of x are in units of 0.1. If I go up to my syntax and change that, maybe I change it from 0.1 to 0.01, so I go in every 100th of an inch, then you'll see this smoothed out real quick, like that. So what we've just done is said, okay, this is the theoretical distribution of sepal length. If we assumed it was a normal distribution, this is what it would look like. Its mean would be right here in the middle at 4.86. Its variance would be 0.118. And we would expect to see flowers somewhere in this range. Technically speaking, no flower is impossible to see, right? It's possible we see a flower with a sepal width, a length of 6 inches. Not likely, but possible. It's possible if we see 1 to 3. It's not very likely. So, that's the thought for question number 1. 2. Question. Why is the normal distribution? It is the distribution function.
Right, but I mean like 1.2 what?
Ah, it's a relative frequency. What that means is it actually doesn't have a scale. It may, but let's not go there for a second. What we would do is say, if we had any two flowers, we could compare which value would have been more likely to occur. Right? So if I had a flower that was 4.5 and a value that was 5.25, it just says, oh, 5.25 is relatively more likely to have occurred than 4.5. That's it. Weird, right?
So what is the scale though?
The scale?
Yeah.
It's whatever it takes so that the area under this curve sums to 1. So this thing is a distribution, meaning that if we go from the entire space of all possible values, that curve has area 1 underneath it. So that's why y can be almost anything. It depends on what x is, what the mean is. Actually, in this case, it really depends on the variance. If this were something that was not continuous, if this was a categorical, if it was x could be 4 or 4.5 or 5, then y would be a probability. And the sum of those probabilities would be 1. Because we have this continuum here, it's a little bit fuzzy as to what y is. Does that help? So I can get in your close. Other questions then? Okay, so that's question 2. How we doing? Question 3 took it up a notch. Sort of. Question 3 said for each observation, right, so this is each flower, report the univariate normal log likelihood for each measurement. Right, so flower 1 had 4 different measures. Each one had a theoretical distribution that looks like this. What I'm asking for there is what the height, so imagine flower 1's, what was flower 1, what was the first flower in that, I guess it's flower 6 in the data, what's their sepal length in the data? Anyone have that in front of you? I'm going to give you an answer. I'm going to take a drink of my Coke Zero. In my Royals cup, I'm not paid by either, but could be. Remote? 5.4. Right here. 5.4. What I'm looking for is the value of the y-axis. The natural log of that value. How do I find it? The Dnorm function. So now, if I go back to syntax, right over here, Dnorm, I know I want the value 5.4 is the thing I'm trying to find the height of. But again, I still have the same mean, and I have the same standard deviation. So if I were to do that, I get the actual height of a value of 0.3375 sub blah blah blah. Come on, move over. You can do it. My finger does not work with this. So 5.4, this is the height of 0.3, whatever I just saw, right? But I'm asking for the log of that height. And sure enough, Dnorm is such a nice friend. Not that R is friendly. I think R stands for rough, isn't that right? Anyway. Whoa! Poor R did not like that. Wow, R is, yeah, Anyway, there is a way that you can put in here log equals true, bless you, and it takes, well, there we go. Running all of it all over again, you can tell the value is negative 1.085. All right, so that's just telling you, bless you again, on the what I'm looking for there for that question is for each one of these 4 observations, what's the relative frequency for a flower? For a measurement, excuse me. Right, but that's relative to all the other flowers for that distribution. Right? So what this was doing was trying to connect a graph of the distribution to the data. That's the purpose of the question. Questions on it. Questions from you on question 3. We're good? Yes, Dan. Yes. Because a distribution can have points of any size. The reality of the distribution. So this is actually a very good question, one that I correct my colleagues on currently. A distribution has to have an area of it under a curve being equal to area equal, which means that area in the distribution has to be positive. But you can have a height that's higher than that. For instance, let me give you a different distribution. Remember the uniform distribution? Remember a uniform distribution? Let's try it between 0 and 1. There's a distribution that looks like this. Right? The uniform distribution, this function was 1 over the upper limit minus the lower limit, so in this case it was 1. That's the height. Right? What if I made the limit of this distribution no longer between 0 and 1, and what if I made it between 0.5, actually 0.25 and 0.75? Now my height has to be different. Right? We can figure it out. It's a rectangle. This is 2 because this distance right here is 0.5. So this height is 2. The height of a distribution is relative to the other variables in it as well, the sample space. It has to make it so that the area under the curve is equal to 1. And that means it can be bigger than 1 because for certain values, you see this right here where it's above 1, the area for those values doesn't take up a lot of space. Right? So they're weighted in with their little space, and then along with everybody else it's below 1 and a lot of space. Does that help? That's right. That's right. Height is relative frequency. It can be any number on the top if it's relative. But the area itself has to be 1. The one constant of it is the area has to be 1. Okay? This actually, believe it or not, that question I correct more frequently than I should from scholars and professors in our field that you're citing. So it's sort of an unfortunate mistake, but it happens. And you're not going to make that mistake now because I like that. So other questions on question 3 or 2 or 1? All right, ready for question 4 then? All right, we want the multivariate normal log likelihood. What was that? Megan is not saying anything. Multivariate normal. That is where things get a little bit more complicated because we need both a mean vector and a covariance matrix. Right? And so it's this multidimensional shape. We also need, was it the fields package to do this? Does everybody remember the library we had to write? There's a library we have to add for this. This is where I need my, okay. So if you don't, there's a thing in RStudio where you can install a package. This is the Dnorm is the function we need for the multivariate normal distribution. At the top of my code in every syntax, this is the automated version of what I'm about to do manually. Okay. What was you said Mnorm T? think the package is Mnorm that I use. There it is, install packages. I was missing an S. Thank you. So now I have the package there. I actually have to load it. All that syntax, again, at the top of your file does all this. You don't have to, if you had copied my file over, it'd be doing this automatically. I didn't copy my file over. So you can see why I copy my files over to start. I don't have it all up in my head. Mnorm isn't? Okay, so we'll just do that. Does dmnorm exist? There it is. Okay, so mnorm is in the starter syntax. And mnorm gives us the function to do the multivariate normal distribution, the height of it, and that is the function dmnorm. Okay? So what, if you want to go with this, it looks very similar to the function we used before with dnorm. The M in there stands for multivariate. Believe it or not, the multivariate one you could have used the whole time because a multivariate with one observation or one variable is a univariate normal. It would give you the same answer. But dmnorm is what this is. It wants you to give you data x, but now x is potentially more than one observation, more than one measure. A mean vector, a covariance matrix, and it wants to know if you want the log. So here's where we get a little bit more complicated. Our mean vector and our covariance matrix come from Livan itself. Okay? So let me give you R is not like this. Let me tell you, if anybody's hard on the homework, it's R. Right? R does not want you getting the right answer. R stands for robust. No, sorry. Trying to be complimentary. You get my stat joke? No, thank you. Appreciate it. The thing we want to do is we did this in question 1. We got the answer for the we have what we need for the mean vector and the covariance matrix, right? We can see all the means for all the flowers. We can see the variance and covariances of all of them as well. We just need to put them into matrix form. So I'm going to do this in an abbreviated sense, and you can do this for a little bit longer sense. There are easier ways to do this than I'm about to show you, but this will get it done. So I'm going to create a mean vector matrix, but I'm going to do it for 2 flowers instead of all 4. Okay? So I could start by saying mean vec. Actually, I'm going to call this mean vector equals, and I'm going to say the word matrix. There's a function called matrix. It creates a matrix that's the right size, that's filled with the first number you give it. So I'm going to go a matrix of zeros. It's going to have number of rows equal 2, number of columns equals 1. So that is my mean vector matrix right there. Right now it's 0, 0. I know that it's not going to be 0, 0. I'm going to plug into it the heights, the means of the flowers from question 1. How do I do that? I have to go for each element and tell it the mean. So let's imagine the first flower, I wanted its mean of sepal length. I would type mean vector. And then in brackets, I would tell it which row, row 1, which column, column 1. And I would set that equal to the value for the mean that it wrote in Livan's output, which was 4.86. Right? And then I just enter it into R, and then if I were to show it off again, it would just have the 4.86 in that first spot. What was the mean of the that was sepal length. Does anyone have the mean of sepal width? Oh, this is row 2, column 1. Anyone have that in their Livan output? 3.34 is the mean of sepal width. So I can just tell it that goes into spot row 2, column 1, and I have my mean vector. I'm just going to do it with 2. Again, now you do it all for all 4. Okay? Okay. What about the covariance matrix? This is going to be, for 2 flowers, what's the size of the covariance matrix? How many rows? 2. How many columns? 2. Everybody's quiet, or just waiting for me? I heard whispering too. Was that Alan? Alan, thank you. Alan gets a gold star today. Gold star. So now in this thing we have 4 numbers to put in. We do the same function. We need to put into it, remember, in order, this thing is going to hold the variance of the first measurement, which is sepal length, the variance of the second measurement, which is sepal width, down the diagonal. All right, so let's put those in first. What is the variance of sepal length from Livan? Livan has that. Actually, we have it already. You told me it. Template's going crazy. 0.118. Right there. So we just filled in one of those 4 numbers. Yeah, I'm actually going to put all 4 numbers in. This is not the efficient way of doing it, but it's going to work. All right. What is the variance of sepal? That was sepal length. What's sepal width's variance? This is row 2, column 2. You want to have the Livan output up? I don't have it in front of me. I don't know the answer. What? 0.114?
Yeah.
Oh, it's the same number. Awesome.
Yeah.
Oh, 0.114. It's not quite it. There we go. Almost close to the same number. So we now have that. The diagonal. What does the off diagonal then need to be? It is the covariance between both flowers. Sepal width and sepal length. Does anyone have the covariance between 2 of those? What? 0.09. Like that? So we know now we have 3 of the 4 numbers. We need to get the one on the top. Well, that's no longer row 2, column 1. That's row 1, column 2. It's the same number. So there we have it, our covariance matrix. How are we doing? So we have a mean vector. We have a covariance matrix. We have 2 of the 3 things that need to go into Dnorm. We just need the data. So what we had before, we had x for the first flower's sepal length was 5.4. What is I'm going to make this matrix of the data. You could do this directly from the data file itself, the data frame. I believe I called it Iris Data 5. That was the name of the data that we're using for the first part. If you wanted to use just the first flower from that, you could put a 1 in the first row for the first row of that. And you wanted to use the first 4 measurements, you could do 1:4. This is the data for that flower. If you go into your data itself, you don't have to. Here's what you can do otherwise. That's for your homework. But for this example, we have a value of a flower that needs to have 2 measurements. I'm just putting the first 2 in. So I'm going to say X is a matrix where the number of rows equals 1. Number of columns equals 2. And in that, I'm going to say the first value of x, so x row 1, column 1, was our first measurement of 5.4, which was the measurement you gave me for the sepal length. Someone have the corresponding sepal width of that first flower in front of them? 3.9. So I'm going to put into this X matrix 5.4 and 3.9. Yeah, 1, 2 there. Thank you. There we go. So now my data look like that, those 2 numbers. So what is this doing? Remember in the bivariate normal, now that distribution is in multiple dimensions, right? And we want to know, we have a flower where we have 2 measurements. How likely is it we observe a flower that has both a sepal length of 5.4 and a sepal width of 3.9? That's what we're asking. What's the relative frequency of it? What's the height of that flower? So we can go put that into Dnorm and get that answer. And now here's where you get to watch me feel the same frustration you do. All right? Maybe. I'm probably going to do this wrong, because the shape of the flower, there's a couple things that can go wrong here. The mean vector has to be one direction and the data has to be another, and I can never remember which direction is which to make this function work. But here we go. Dnorm. We're just going to give it the x mean vec equals mean vector. That's our mean vector. Cov mat equals cov matrix. That is our covariance matrix. And it, oh, I gave it the wrong thing. I need to give it mean. Mean and the names of it, mean and varcov. So the names that you put afterwards, this is mean, this is varcov, they have to match what R expects them to be in the not help. And now it does not, it tells me it is a mismatch of the dimensions of x and mean. That means I just take the transpose of x, this t function. Oops, I didn't like that either. Maybe I take the transpose of the mean vector. There it is. See? Do you see where if you get these errors, you can get it to work. So what we did there, we have to have it. This is where we talked about matrix algebra last week. I said the transpose is our little trick to get everything to work out. It's sort of flexible. It's kind of context specific. This function wanted the mean vector to be a row vector, not a column vector. The data can be a row vector. The mean vector wanted to be a row vector. Once you put those two together, it says, oh, I know what to do now, and it goes and gives you the height. That normal, multivariate normal distribution with all the matrices in that we did before, did all that. So what's the point of that? That's the height, right? That's the height for that one observation, right? So you're saying if I found the mean of my sample to be, whatever, for this one flower, 4.86 for the for sepal length, and 3.34 for sepal width, and I found the variance to be these things, here's what the likelihood, the relative frequency for this one flower would be based on. So basically, how far away is it from the mean in likelihood units, right? The distance. I know we were talking about that earlier today, right? For this flower. The higher that number is, the more it's closer to the mean. The lower that number is, the farther it is from the mean. I just realized there's one little catch. I asked you for the log likelihood for this. You can put log equals true at the end of it, and it will give you the log of that number. So, okay. So, all that gets you the last question. Question 5 for part 1. And it says, for all of those 5 observations, take those logs and add them together. And actually, those numbers I found, thanks to some of you, are very small, are very similar. Those numbers are almost the same, and that's because there's not a lot of variation in our flowers. But take the sum of those 5 numbers. You get now a log likelihood. That is your sample log likelihood. It says compare that with the value from number 1, the H0 log likelihood from number 1. They should be the same. They should be the same because that's the same thing that Livan's doing to figure out your estimates for the mean vector and the covariance matrix. Okay? Livan is basically saying, you know, what you did to answer number 4, you plugged in numbers for the covariance matrix, you plugged in numbers for the mean vector, and you went and grabbed your data and said, how high, what's the height of each of these flowers? Right? And then you added all of them together. That is exactly what Livan was doing. The only difference was it plugged in different values for each of the variances and covariances and means. It tried out a whole bunch of different ones, but then it settled on the ones that figured out the height. So my purpose in doing all that was to get you thinking about how all this is working, because all of a sudden when we talk about what we're doing with today, we're going to, each model that we do in structural equation modeling, when we have this normal type data, implies a very specific covariance matrix and a very specific mean vector. And in fact, that implication and all the things that we interpret, some things like beta weights and regression or factor loadings, if you've heard that term, all the terms that are out there, unique variances, beta weights, factor loadings, all that show up in one of those 2 places, either in the mean vector or the covariance matrix. So you make a model, it implies this. Because of that implication now, Livan isn't trying the means and variances out, it's trying those parameters. It tries the parameters, from them it gives you a mean vector covariance matrix, and then from that gives you a likelihood. So this is the point of the first part of the homework. Questions on those on questions 4 and 5 as we move on. Any questions? Was that me? No, thankfully. Is that you? No. Sorry, again, my phone is on. It's a weird thing to teach with my phone on, so I'm on call. 30 days from today is Lisa's due date, so we will see if the next generation comes sooner rather than later. So does this help you frame your homework a little bit differently now as you go forward? Okay. The second part of the homework is a model comparison task, and we will talk about that as we go through class today. Okay? But now we're up against the break. So let's take a break for 10 minutes, come back around 10 minutes from now, and we'll get it started, all right?